as promised in the previous video, here's an example that's going to look at whether or not a graph is continuous at some specific values. So first off, we're going to graph this massively fun piecewise function f of x. So when x is less than or equal to -1, f of x is +1. So we get the graph looking like that. Between -1 and 0, our graph is -x. So y-intercept of 0, slope of -1. So it looks like that. And this would be an open dot. This would technically be an open dot too, but it got filled in by the first part right here. I want you to pause the video right now and try to continue graphing this function. Okay, so hopefully you pause the video. Hopefully you are giving this a try. But this third part, f of x is 1 if x is 0. So we're going to get a solid dot right there. And then -x going from 0 to -1. 0 to +1. So it continues that way. So we have two open circles, one at x equals 0, one at x equals 1. And then we have f of x is 1 when x is greater than 1. That's a fun little graph. That's a fun little graph. Look at it. It's beautiful. So now we have to find the limit as x approaches -1, 0, and 1. So as x approaches -1, is the graph going to the same place both directions? Those little blue arrows I just put on there. Yeah, so the limit exists. The limit is equal to 1. Now it also asks over here, is f of x continuous at these values? So my question to you is, what is f of -1? Because remember, the limit has to exist. It has to be defined for that value, and those two things have to be the same. So f of -1 is 1. So is it continuous at x equals -1? Yes, for -1. X equals 0. So as we approach 0 from both directions, are we approaching the same place? Yeah. As x approaches 0, f of x approaches 0. What is f of 0? F of this value down here that we're approaching. Well, it's equal to 1. And these two values are not the same, so we're not continuous at x equals 0. And finally, as x approaches 1, as we approach 1 from both directions, are we approaching the same place? And you better be saying, oh no, we're not. So what does that mean? Well, that means that the limit does not exist or it's undefined. We are not approaching the same place from both directions. And since we're not approaching the same place, the same spot from both directions, it can't possibly be continuous at x equals 1. So this graph is only continuous for those three values we were asked to check at x equals -1. All right, so determine a value for k so that f of x is continuous at x equals -1. Well, so if we look at a graph of this, what you'll see is a parabola, and that should be a little surprising since this is a cubic function. So if it's a parabola as a graph but a cubic function, that means that there might be a hole somewhere, ladies and gentlemen. And what you find is that there's a hole at x equals -1. That's why it's not defined there. So what we have as a graph is Looks a little something like that with a hole over here. Now, how could we figure this out algebraically? Well, let's take this numerator and try to factor it. And what we're hoping is that there's an x plus 1 in the denominator to cancel out with the factor in the numerator, creating this hole in the quadratic graph. And to factor this guy, it's a little bit fun. I'm going to add 2x and subtract 2x. And you might ask, well, why would you want to do that? Well, bear with me. I'm going to factor an x out of the first three terms. And then I'll factor a negative 2 out. And what I did was I created a trinomial quadratic that is factorable. X minus 2, x minus 1. And you might be looking at this going, well, that's not helping a whole lot. Well, both of these terms now have x minus 2 as a factor. In the leftovers, we have x times x minus 1 minus 2. Bear with me. Distribute. And what we now have is x minus 2 times x minus 2, x plus 1 over x plus 1. There's my factor canceling, giving me the whole at x equals negative 1. And this is equivalent to x minus 2 quantity squared. And that is the graph that we're looking at here. So the question becomes, if we were to assume f of x was x minus 2 quantity squared, what would that point be? What would be the value that would fill it in? So we get negative 1 minus 2 squared, which is 9. So we have a hole at negative 1, negative 9. So that means that k needs to be 9 to fill this thing in. Last example here, using a graphical display calculator, graph y equals x over the square root x squared plus 1. Clearly show asymptotes and use a domain of negative 20 to 20. So, graphing calculator, here we are. There is our curve. And we want to graph it from negative 20 to 20. And we could come in and grab the axes. And, wow, that doesn't do a whole lot because it shrinks the whole graph. Let's resize our window to something that makes sense for this graph. For my x's, I want to go negative 20 to 20. And we'll set our x scale to be 1. Our y minimum, let's make our y minimum be negative 2, and our y max be positive 2, and we'll have our y scale be, let's go 0.1. There we go. That's looking better. So how do we create this on our page? Well, we're going to go and look at our table. And we can plot a whole bunch of points going from negative 20, or we could go even further than that. But we just want to go from negative 20 to positive 20, grabbing some points out of this table. And what we want to know is, well, what's the asymptote? Well, the asymptote is going to be what this graph is approaching as x gets really, really huge. So let's get really, really huge. Roll down this table. What's the graph approaching? Well, it appears to be approaching 1. That's a big long decimal. It's getting close, close, close to 1. Same thing the other direction. There's a big long decimal that's getting close, 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 close to -1. So we have two asymptotes, horizontal asymptotes. Y equals 1 and y equals -1. So we can say that the limit as x approaches infinity, we'll call this f of x is equal to 1. The limit as x approaches -infinity of f of x is equal to -1. And those are my asymptotes. My asymptotes are y equals 1 and y equals -1. In the next section, we'll look a little bit more at asymptotes, and we'll look at some properties of limits, as well as how to find limits algebraically.